China built a stadium that blooms like a flower, and FIFA hasn't been able to stop staring since. 11 stadiums, $1.7 billion. Roofs that move on magnetic levitation tracks borrowed from bullet trains. Foundations drilled 800 piles deep into the seabed. And a double-helix ramp that spirals for an entire mile to a rooftop view of the open sea. That's roughly the height of 233 Statues of Liberty stacked underground. You heard that right, just to hold one stadium in place. What China has built isn't just infrastructure. It's a statement that the rest of the world is still trying to process. And it all starts with a flower that nearly died. Picture the most expensive stadium ever conceived in China. 100,000 seats, 12 steel petals arching outward from a central core, each one wide enough to shelter a city block. The whole structure designed to look from above, from a passing plane, from satellite like a lotus flower, in full bloom. The price tag, $1.7 billion. The man writing the check, Xu Jiayin, the founder of Evergrande, the most powerful football club in Chinese history, and at that moment, one of the richest men in Asia. Evergrande wasn't just building a stadium. You have to understand what this project meant. This was a declaration, a physical, steel and concrete announcement that Chinese club football had not just arrived on the world stage, but that it intended to build a throne and sit on it. No other club stadium on Earth would be this large. No other club had spent anything close to this amount. The Lotus wasn't a design choice. It was a power move. But then came the most devastating news of all. In 2021, Evergrande collapsed under more than $300 billion in debt, the largest real estate implosion in the history of the world. Work stopped overnight. The cranes went silent. The workers went home. And the Lotus sat there on the outskirts of Guangzhou, half-finished, steel petals frozen mid-bloom, rusting quietly in the humid air. You could see it from the highway. A $1.7 billion skeleton, a monument to overreach, the most expensive unfinished building in Chinese sports history, and nobody knew if it would ever be completed. Then the Chinese government stepped in and everything changed. The stadium was seized, transferred to Guangzhou City Authority, and handed new funding with a single directive: finish it. Same design, same scale, same 12 petals. Because the design was too extraordinary to abandon, and because China had something to prove, teams returned, cranes restarted, and over the following months, you watched the Lotus finish blooming. The steel skin completed, the seating filled in, the facade sealed, until the largest football stadium in China finally opened its doors. Not as a monument to one billionaire's ego, but as a public asset belonging to the entire city of Guangzhou. Here's the payoff. The stadium that was supposed to prove that Chinese football money could buy anything, instead proved something far more interesting: that when Chinese engineering gets state backing, not even the largest bankruptcy in world history can stop a flower from blooming. But if Guangzhou showed you what ambition looks like when it has unlimited funding, the next stadium is going to show you something that might actually impress you more: what Chinese engineers can achieve when they decide to use less. You've just seen what happens when China throws $1.7 billion at a stadium and refuses to let it die. Now forget the budget, forget the scale, because the next stadium on this list did something that, from a pure engineering standpoint, is arguably more impressive. It built a more complex, more beautiful, more dynamic structure than the bird's nest, and used 67% less steel to do it. You heard that right. Nearly 2/3 less steel than the most famous stadium on Earth. The Hangzhou Olympic Sports Center is also a lotus, also a flower, also a roof that opens like petals tracking the light. But where most people assume that Chinese megastadiums are built on the logic of more material, more money, more mass, Hangzhou's engineers asked a completely different question. They asked whether the same spectacle could be achieved through smarter geometry rather than sheer weight. The answer was a petal roof system that distributes load through curvature and tension rather than through mass. Instead of stacking steel until the structure holds itself up by brute force, the roof uses the mathematics of curved surfaces, the same principle that makes an eggshell stronger than it has any right to be. to carry enormous loads with a fraction of the material. The petals don't just open for aesthetics. They move to manage light and ventilation, making the building breathe. But this was just the beginning of what China's second generation of stadiums was capable of. Because Hangzhou isn't just a pretty building, it's a turning point. It's the moment China's stadium engineers stopped trying to outmuscle the first generation and started trying to outthink it. And once they made that shift, the ideas that followed got stranger, bolder, and harder to believe with every single stadium. The next one took its design cues from a fleet of ships that sailed 1,000 years ago and built it in under 2 years. You're standing inside a stadium whose roof curves aren't drawn from a computer algorithm or a modern architect's sketch pad. They're drawn from the hull of a Song Dynasty merchant ship, a vessel built over 1,000 years ago, when Chinese shipwrights had already mastered the art of bending wood and rope into curves that could carry enormous loads across open ocean. The engineers here looked at that 1,000-year-old tradition and asked a simple question. If it worked on water, why wouldn't it work in steel? The answer is wrapped around you in every direction. But here's where it gets interesting. Guangzhou is brutal in summer, the kind of heat and humidity that makes you feel like you're breathing through a warm, wet cloth. Most stadiums in this climate solve that problem with industrial air conditioning, massive systems that blast cold air into a sealed bowl and burn enormous amounts of electricity doing it. The Greater Bay Area Sports Center doesn't do that. Instead, the curves and overhangs of those Song Dynasty hull profiles are engineered to channel natural airflow through the seating bowl, pulling heat upward and out the way a chimney draws smoke using thermodynamics instead of electricity. Passive cooling, built into the geometry of the building itself. Then came the detail that should genuinely stop you in your tracks. This entire stadium, the curves, the passive cooling system, the structural complexity of translating ancient shipbuilding into modern steel was built in under 2 years. Not rushed, not compromised. Delivered in under 2 years through prefabrication strategies and parallel construction workstreams, so precisely coordinated that the construction process itself was an engineering achievement as ambitious as the building it produced. And if you think building in under 2 years on reclaimed land sounds difficult, the next stadium was built on something far more unforgiving, the floor of the sea itself. You know Kai Tak is one of the most infamous airport approaches in aviation history. A descent so low over Hong Kong's rooftops that passengers could see what people were eating for dinner through apartment windows. The runway ended at the edge of Victoria Harbor. Planes landed, braked hard, and stopped just short of the water. It was terrifying, legendary, and eventually replaced. And on that same reclaimed land, sitting on the edge of that same harbor, China built a 50,000-seat stadium. The ground beneath it isn't solid earth. It's decades of landfill sitting on top of soft marine sediment, and below that, seabed. You cannot build a structure of this weight on that surface without first reaching down through all of it and finding something solid to stand on. So, the engineers drove 800 piles into the seabed. 800 individual foundations, each one bored and anchored into rock far below the harbor floor. Each pile head aligned with enough precision to carry the enormous load of the stadium above. The operation alone was a construction project worthy of its own documentary. But the foundation isn't even the most remarkable thing about Kai Tak. The roof is 4,800 tons of retractable steel, roughly the weight of 3,000 family cars mounted on a moving mechanical system that closes completely in 30 minutes. That deadline isn't arbitrary. In Hong Kong, a typhoon signal can go from advisory to critical in less time than that. The roof isn't a luxury. It's a weather defense system, engineered to the specific threat profile of one of the most storm-exposed cities on Earth. Kai Tak is dense, pragmatic, and quietly extraordinary, exactly like the city it sits in. But what comes next takes a technology you associate with bullet trains doing 200 miles per hour and applies it to something you would never expect. You've watched a roof close against a typhoon in 30 minutes. Now imagine a roof that moves in complete silence. No grinding, no shuddering, no mechanical protest of any kind. Just massive steel panels drifting across the sky like clouds, slow and inevitable, as if the laws of friction simply don't apply here. That's not imagination. That's Chengdu Fenghuangshan Stadium on any given match day. The retractable roof doesn't move on conventional rails. It moves on. Magnetic levitation tracks the same technology that powers China's high-speed bullet trains across thousands of miles of track at 200 miles per hour, applied to the roof of a 60,000-seat football stadium. The panels are suspended fractionally above their tracks, using electromagnetic repulsion, eliminating contact, eliminating friction, and eliminating the mechanical wear that makes conventional retractable roofs expensive to maintain and prone to failure over time. But here's what you need to understand about why this exists. China didn't invent Maglev for stadiums. It built one of the most extensive high-speed rail networks in human history, and in doing so, it accumulated decades of deep engineering expertise in magnetic levitation systems, expertise that lived inside state research institutions, railway engineering firms, and infrastructure agencies. Chengdu Fenghuangshan is what happens when a country's transport engineers and its stadium architects end up in the same room, and someone asks, what else could this do? The technology jumped lanes. And the result is a stadium roof that doesn't just function better than anything built before it. It moves in a way that makes every other retractable roof on Earth look clumsy by comparison. And if Chengdu showed you what happens when China transfers its most advanced transport technology into sports architecture, the next stadium took a crowd flow problem and turned it into the most extraordinary arrival experience in football. You don't enter Dalian Suoyuan Stadium through a gate. You don't funnel through a concourse or queue at a bank of escalators. You walk onto a ramp and you keep walking. The ramp spirals around the entire exterior of the building in a double-helix formation, two paths winding in opposite directions simultaneously, 1 mile long from ground level to the roof. Arriving fans spiral up one helix. Departing fans spiral down the other. The two crowds never cross paths, never bottleneck, never compress into the crushing pinch points that have caused tragedies at stadiums around the world. But this wasn't just a crowd flow solution dressed up in interesting geometry. Crowd management in a 60,000-person stadium is one of the hardest problems in sports architecture. Every level transition, every stairwell, every escalator bank, every choke point where a crowd must compress to pass through is a potential disaster waiting for the wrong conditions. Traditional stadiums stack these transitions on top of each other and hope the timing works out. Dalian eliminated the transition entirely. The ramp is a continuous surface. People move at walking pace across a single unbroken path, and the double helix geometry means the system handles both arrival and departure simultaneously without interference. Then you reach the top, and the engineering problem becomes something else entirely. The ramp deposits you on a rooftop promenade with an unobstructed view of the Yellow Sea stretching to the horizon in every direction. You've just walked a mile upward through a spiral of steel and concrete, and your reward is standing on the roof of a football stadium with open ocean in front of you and the wind off the water in your face. Dalian took a circulation problem, solved it elegantly, and then turned the solution into the best part of the building. The next stadium didn't have the luxury of building on flat coastal land. It had to build on a coastline that fights back. You think you know what a coastal city does to a building. Salt air gets into the steel, moisture follows. The corrosion starts slow, invisible, working its way through standard construction materials over years, until what looked solid starts to compromise from the inside out. Most stadiums in coastal environments spend enormous amounts of money on maintenance cycles, repainting, resealing, and replacing structural elements that the sea has quietly been eating since the day they were installed. Qingdao's engineers looked at that problem and decided they weren't going to fight the sea on its own terms. They were going to build a stadium the sea couldn't touch. The structural steel at Qingdao Youth Football Stadium is marine grade, the same specification used in offshore oil rigs sitting in open ocean, exposed to salt, spray, and storm surge 365 days a year. Not similar to oil rig steel, not inspired by it, the same standard. Then they looked at the drainage problem. A coastal pitch in a city that receives heavy seasonal rainfall needs to shed water faster than nature delivers it, and they engineered the drainage system to airport runway. Specification: the same capacity standard used for surfaces that must stay operational during the kind of downpour that shuts down roads. And then they built the entire thing in 3 years. Not 3 years of calm, controlled construction in a forgiving environment. 3 years of building in a coastal zone that corrodes formwork, warps untreated materials, and turns an ordinary construction site into a constant battle against the elements. The next stadium faced a threat that makes salt air look gentle. It was built directly on top of one of China's most active earthquake faults. You need to understand what the ground beneath Lanzhou actually does. The lowest plateau in Gansu province sits in one of the most seismically active regions in all of China. The 2008 Sichuan earthquake, the one that killed nearly 70,000 people and leveled entire towns, radiated its destruction across this same stretch of the country. Building anything here carries risk. Building a mass-gathering venue where 60,000 people sit shoulder to shoulder carries a moral weight that goes far beyond architecture. So Lanzhou's engineers didn't just meet the standard seismic building code. They went to the most demanding standard of earthquake protection that exists in civilian engineering, the specification used for nuclear power plants. The stadium sits on a base isolation system borrowed directly from nuclear construction. The entire building rests on a network of isolators positioned between the structure and the ground beneath it. When the Earth moves during a seismic event, and in Gansu province, it will move those isolators, absorb and dissipate the energy before it reaches the building above. The ground shakes. The stadium doesn't. The resonant amplification that turns a tremor into a structural collapse is interrupted at the foundation before it ever travels upward. But here's what that actually means for the people inside. If an earthquake strikes during a match, 60,000 people are sitting inside one of the most seismically protected civilian structures in the country. Lanzhou didn't just solve an engineering problem. It made a promise to every single person who walks through its gates. The next stadium didn't have a fault line to contend with. It had something, in some ways, even harder: 400 feet of empty air where the foundation was supposed to go. You've heard Chongqing described as unbuildable. It's not an exaggeration. The city is carved into a landscape of mountain ridges and river gorges so extreme that streets run at angles other cities wouldn't attempt. And buildings sit at elevations that would be considered cliff faces anywhere else in the world. Chongqing didn't grow despite its terrain. It grew through it, around it, and sometimes directly into it. And when the city decided it needed a football stadium, it picked a site with a 400-foot elevation drop across its entire footprint. There was no flat ground. There was no level pad to pour a foundation on. There was just a hillside falling away beneath where the stadium needed to stand. Conventional stadium engineering assumes one thing above everything else: that the ground is level. Every load calculation, every column spacing, every foundation depth is built on that assumption. Longsing threw it out entirely. Different sections of the stadium sit at radically different depths. The structural columns on the downhill side are dramatically taller than those on the uphill side. The load paths through the building shift direction and magnitude depending on which section of the structure you're standing in, because every section of the structure is essentially a different building. All of them merged into one coherent form at the top. Before a single seat went in, the construction team was simultaneously building multiple structures at multiple heights and connecting them mid-air. Think about what that coordination actually demands. Separate engineering teams working at separate elevations, each solving a different structural problem, all of them required to meet at precise connection points where their work becomes one unified building. A single miscalculation at any junction would have sent the entire merged structure out of alignment. The margin for error was effectively zero, but Chongqing has always refused to be constrained by geography. And the stadium reflects exactly that. A city that looks at a 400-foot drop and sees a foundation, not an obstacle. The next stadium didn't fight its environment. It turned its own geometry into the solution. You're looking at a building that shouldn't hold together. The facade is a lattice of triangular glass panels, no two sitting at quite the same angle, fracturing light differently at every hour of the day, a crystalline surface that looks more like a shattered gemstone than a sports venue. Your instinct says this geometry is unstable. Your instinct is wrong. Those triangular panels distribute wind load more efficiently than any conventional flat curtain wall ever could, because the angles redirect force laterally rather than letting it concentrate at fixed points. The crystalline look isn't decorative. It's structural logic expressed as something breathtaking. Every panel angle was calculated not just for appearance, but for performance. The facade is simultaneously the most visually striking and the most aerodynamically intelligent skin on any stadium in China. But the geometry created a problem nobody could ignore. Hard-angled surfaces scatter sound in patterns that standard acoustic models can't predict. Shenzhen required specialist acoustic engineers to map every single reflection path inside the bowl and retune the internal geometry so that 60,000 people could hear clearly from every seat. What looked like an artistic choice forced one of the most complex acoustic engineering exercises ever applied to a sports venue. Shenzhen is a city built on the conviction that things others considered impossible were simply things nobody had tried yet. It got exactly the stadium it deserved. And now you've arrived at the one that started everything. You already know the bird's nest. You've seen it 1,000 times. But familiarity has dulled the shock of it, so let's go back to 2008, when none of this existed yet. A country stepping onto the world stage for the first time at that scale. A design so structurally unconventional that the engineers building it had never done anything remotely like it. 42,000 tons of steel woven into an organic lattice, with no single load-bearing spine every beam carrying load. The apparent randomness of the weaving a precisely calculated structural system that distributes force across thousands of different paths simultaneously. It worked. The world stared. And something shifted inside Chinese engineering and architecture that has never shifted back. The bird's nest didn't just host the Olympics. It gave an entire generation of Chinese engineers a reference point and a single burning question: what could we build if we pushed past this? Before 2008, world class meant imported foreign architects, foreign firms, foreign ambition planted on Chinese soil. After 2008, Chinese firms started asking what they were capable of entirely on their own terms. The bird's nest was the permission slip. And the answer came back in the form of every stadium you've just watched unfold in this video. Every lotus, every magnetic levitation track, every mile-long spiral ramp, every pile driven into the seabed. China didn't build these to pass a FIFA checklist. It built them because it decided that if it was going to build stadiums, they would be the most extraordinary stadiums in human history. And looking at what it has produced, it is very hard to argue that it hasn't already succeeded.